This is Premier Aerodynamics podcast number 22, and today we're talking about noise of high-speed trains. So this is going to be a two-part podcast. Number 22 is going to be the noise reduction of high-speed trains, and podcast number 23 will be the noise reduction of high-speed trains. And to look into both of these phenomena and how to do this, we're going to look at the research article called Research on Aerodynamic Noise Reduction for High-Speed Trains. So the trains, when they are going very slow, the noise coming off them is not very loud. There's not a very high decibel level. But as you speed up, they get louder and louder. And as we'll go through in the paper, it becomes very non-linear. So let's talk about how noise is produced from a train, because there are a lot of different parts that do create noise and why this noise does get created and to begin with. So for those who aren't quite aware how acoustics and aerodynamics fit together. So acoustics pretty much all the time comes from unsteady aerodynamics. So they're very intimately coupled, and this has led to a field called Aeroacoustics. And it's almost impossible really to divide acoustics from aerodynamics because of how coupled they are. So one entails the other. So let's look at this paper. They say that the near-field unsteady flow around a high-speed train was analyzed based on delayed detached eddy simulation, so DDES. That's a CFD method. It's a fairly accurate one. It's not getting really accurate, but in terms of our computational power, it's probably the most accurate we can do in practice. And then they say an aerodynamic noise model for a full-scale high-speed train, including 3 coaches with 6 bogies, 2 intercoach spacings, 2 windscreen wipers, and 2 pantographs were established. So let's go through each one of these different aspects to talk about what they are. So 3 coaches means that there are 3 compartments. Like in a train, you have each compartment that you can walk through and sit down in whichever one. So that's what they mean by that. 6 bogies. A bogie is the little wheel section. So on a train you have like sections where they have 3 or 4 wheels right next to each other. That's a bogie area. Then the intercoach spacings, that's the spacing between 2 coaches. And then the windscreen wipers are obviously windscreen wipers. And then pantographs. So the pantograph is that like little structure that pops up on the top of a train and touches the electric cable above. So that pantograph section, you not only have that little structure that comes up, you also have the transformer and whatever else on top of the train. So these are all very important aspects. There are more aspects as well that we'll look at a bit later. But all these not only affect the acoustics, but also the other ones will affect as well. They go on and say, based on the analysis, so this is for the noise reduction, which we'll talk about later in the second podcast, they designed a low noise structure for a full-scale high-speed train with an average sound pressure level of 3.2 decibels lower than the original one. So that's actually a very big reduction. It may not seem a lot, but the decibel levels, they operate on a log scale. So even if you drop it by 1, that's still quite a lot. In addition, the accuracy of the aerodynamics noise calculation method was demonstrated via experimental wind tunnel tests. So what they're saying is that their CFD that they did, they validated it with their experiments, and they found that it lines up very well. So they can use their CFD to analyze the flow in more depth. Moving on, they say with the high running speeds of high-speed trains, problems that can be neglected at low speeds become sufficient to limit improvements in train speed. Shen, an author, notes that the dynamic environment of an ordinary train depends mainly on machinery and electricity. By contrast, the dynamic environment of a high-speed train depends mainly on the aerodynamic forces. Therefore, aerodynamic noise becomes the greatest limitation. And it becomes so great that you can't actually run the train faster than a certain speed. Otherwise, it becomes unsafe for passerbys and people who live near train tracks. They go on and say aerodynamic noise rapidly increases with increasing running speeds, becoming the main noise source for high-speed trains. Indeed, the sound power of aerodynamic noise grows as the 6th power of the running speed. So it's not like drag or force where that's squared to the 2nd power. This is the 6th power, so that's massive. So once you increase the speed by even 10 kilometers per hour, that's a massive increase in noise. The noise that exceeds the standard requirements has become one of the main limiting factors of train speeds, restricting the sustainable development of high-speed railways. The main aerodynamic noise sources for high-speed trains are as follows. The pantograph, so that's that electric little cable that comes up and touches the wire, plus its surrounding infrastructure to get that power and use it. And then you have the first bogie, so that's the first wheels of the train, the power head nose, so that's the front of the train, the head cow catcher. So on the train, those in classic trains, you have that little iron triangle sort of thing on the front. That was called a cow catcher, and I'm guessing they named it back then to catch any livestock that had fallen on the trains and get rid of them. Not very pleasant, but whatever. The train head, the train tail, the train windows, the train doors, the intercoach spacings, and the bogie skirt boards. So pretty much everything on the train, in other words. These aerodynamic noise sources can be classified into two types. The first type corresponds to noise rated by a steady flow structure. For example, the steady vortex shedding immediately behind the pantograph that can generate a significant aerodynamic noise, which strongly contributes to the overall noise. Moreover, certain cavity structures on the surface of high-speed trains can also generate aerodynamic noise. The other type of noise source refers to noise emitted by turbulent fluctuations, which occur mostly in the turbulent boundary layer near the surface of a high-speed train or at locations where flow separation occurs. So we have two different general noise sources, the steady and the unsteady. Reducing the aerodynamic noise of high-speed trains requires reducing the noise of the main noise sources. Rough areas on the train severely disturb the airflow at high speeds, thereby generating complex flow separation and vortex shedding phenomena. The resulting power fluctuations in air pressure in the far field translate into aerodynamic noise. This source can be predominant in the case of a high-speed train that is running behind a 4-meter high noise barrier as the pantograph is higher than the noise barrier. So what they're saying here is, you have some trains where they put a noise barrier up, so it will shield most of the noise coming from a train. But then you have the pantograph, which is still creating a lot of noise because that's above the train, and that's still going to be impacting pedestrians and passerbys. So it's not feasible. You have to reduce this noise still. So Sueki and others conducted full-scale and wind tunnel measurements of a PS207 pantograph. They're installed on the Shinkansen Series E2 1000, so that's a high-speed train in Japan. It's equipped with a porous material and demonstrates that a noise reduction of 1.9 decibels at 360 kilometers per hour could be achieved, with a significant noise reduction of 5 decibels at the 1/3 octave band center frequency at 250 hertz. So that's a very big reduction based on having a different material to make up this pantograph, a porous material. So they say the results show that the material properties of a pantograph significantly influence its aerodynamic noise. So it's not just the shape of it, but also the porosity. The bogie is one of the main aerodynamic noise sources for a high-speed train. So they're the wheel carriages kind of thing. However, because of the complex structure and disordered distribution of the flow field around a vortex, bogie aerodynamic noise is poorly understood in your calculations. So it's very difficult to accurately simulate because you just need so many cells and so much time and so much going on. We'll get into that in a little bit. And then some other authors, so Wakabayashi and others, and Kurita and others, performed noise tests on a Fastech 360S train with full skirt boards for all the bogies, and found that the noise from the lower part of the train reduced by approximately 1 decibel compared to the Series E2 1000 train. So even though you put on these boards, which really alter the train a lot, you get a 1 decibel reduction, which is good, but it's not a huge amount considering that, as you increase the velocity, you're going to be increasing the noise a lot. So it needs to be a bit more than that. So 1 decibel is good, but you need more. And then some other authors, Yamazaki and others found that the intercoach spacing is also a major noise source for high-speed trains. So when you have the distance between two coaches, that affects the noise. And we'll talk about that in a second. Before we go any further, I just want to say, make sure you check out the Atmosphere Hawk and the PRV system that we make here and the traversers that we make here at Premier Aerodynamics. These are all experimental instrumentations to help your experiments be better. Check out the courses we put on in CFD, experiments, and theory to make you a better aerodynamicist, and check out the International Aerodynamics Conference we put on every year to help you interact with other aerodynamicists and build your network. All the links can be found in the description. So moving on, they talk about at length how they simulated this train. One thing that I want to talk about is how difficult it is to simulate the noise, not just on trains, but on anything. So one of the major problems that people run into is, first of all, that most noise is unsteady. Secondly, that how noise is generated and propagates is very complex. So you have something called monopoles, dipoles, quadrupoles, octopoles, and who knows what else. So what all these things mean is that depending on where this noise is coming from, it's radiating in different ways. A monopole means that this noise is radiating in all directions equally. And very few things are true monopoles, because even some things that do approximate monopoles, they only radiate noise equally in all directions for certain frequencies. Other frequencies are not that good. Then you have something called a dipole, and these are more complex. This is where, imagine an infinity symbol. This is how sound radiates out from a dipole. It's not concentric, it's in this infinity symbol and it just gets bigger. That's more complex. Then you have quadrupoles. Now, a quadrupole is, imagine the infinity symbol and get another infinity symbol, rotate that 90 degrees and superimpose it on the first one. Now you have this kind of 4-point pattern and it radiates out in that way. Then you have octopoles, where you put in another infinity symbol effectively and rotate it 90 degrees, so it's orthogonal to both of those directions, the original two. And then you have octopole. And these are all, and as you go higher up in these poles, it gets more and more difficult to simulate. So trying to do RANs and steady, it's not going to work. You're not going to get very good approximations. And even on, actually, I knew a researcher, he was working on noise generation from airfoils, from foils in general. And even for a very simple shape like that, it was difficult to properly simulate the noise coming off of that when you're using RAN. So you have to go to DES. So it can be very difficult, but these people found out that they could accurately simulate that noise production with their CFD, and they go into it and talk about it. So they're going to say characteristics of the aerodynamic noise of high-speed trains. The main noise sources for high-speed trains are predominantly dipole sources. So as I was talking about before, it's kind of like an infinity symbol is how this noise radiates out. And the dipole sources on train surfaces are determined by the pressure fluctuations on the train surface. The surface turbulent kinetic energy distribution in the pantograph fairing region is shown in Figure 8. So this shows the turbulent kinetic energy, which is a major source of noise. They say that substantial turbulent kinetic energy is distributed at the points of transition between the leading edge of the pantograph fairing and the folded pantograph, the fairing region, and the second intercoach spacing. So in other words, if you look at all that infrastructure on top of the train, whether you're getting a lot of noise is obviously the pantograph itself, so that wire thing. Then at the start of all that infrastructure, at the back of it, and then at the intercoach spacing, which is usually following this pantograph. Noise radiation in the region of the lifted pantograph is enhanced by impinging turbulence and vortex shedding. So everything that's coming from upstream is, with all this vorticity, is impacting other surfaces, and that's creating even more noise. So it gets very complex. The second intercoach spacing with high turbulent kinetic energy is also considered to be a major noise source. So even though it's not that aerodynamic, but it is fairly smooth compared to like the bogies and the pantographs, these regions still do create a lot of noise. The flow around the pantograph region is characterized by considerable coherent alternating shedding of vortices with different sizes and orientations. So because you have quite a few different vortex sizes, you do get different noise frequencies. In many engineering applications, turbulence poses broadband noise problems. So let's talk about this. So what's the difference between broadband and tonal noise? So broadband noise, if you imagine, let's say, just the general frequency spectrum between 20 hertz and 200 hertz, let's say, or whatever. And broadband noise is one that you're going to get a lot of noise at all these different frequencies. So it's not just one tone. Tonal noise is where you get noise from just one tone. So let's say 43 hertz or whatever. So that's the difference between broadband and tonal. And because you have, in these applications, a lot of different vortices coming off of different areas and impacting each other, they're not really uniform, they're not homogeneous. So you're going to get more broadband noise. To get a tonal noise, you usually need to have one dominant structure forming and continually forming like that. And they say here, There is no obvious dominant frequency band, and the wide band range of noise or sound energy presents a continuous frequency distribution. Radiated aerodynamic noise is a typical type of broadband noise, which exhibits a frequency spectrum covering a wide range of frequencies, as I mentioned. Then they have some CFD for those listening. By the way, we are on Spotify, and Spotify just recently let us put on videos. So our podcasts also have videos showing these papers and these figures. So if you want to look at these pictures, you can go on Spotify and watch and listen to the podcast at the same time. Alternatively, you can just listen to my descriptions of them. So in this paper, they have the acoustic power level, so the decibels of different regions of the train. And what they found is that the bogies, the further upstream these bogies are, generally the more noisy they are. So the closer to the nose of the train. The pantograph, those wire structures, they make a lot of noise, almost overriding everything else really on the train to some extent. And interestingly, the intercarriage spacings between, let's say, the first and second carriage, the part that's actually making a lot of noise is not the trailing edge of the first carriage, but the leading edge of the second carriage, which kind of makes sense because the flow is actually impacting that second one far more than the upstream one, the trailing edge. So those are interesting graphs there. And they go on to say, the main noise sources on a high-speed train are the pantographs, the head windscreen wiper, the bogies, the pantograph fairing region, the head cow catcher, the windward side areas of the bogie regions, the intercoach spacings, and the power head nose. So pretty much anywhere where there's a discontinuity in the geometry, there's noise being produced. The noise sources on a high-speed train are located where the airflow is easily separated and where the turbulent motion is strong. And they have a really cool figure here. It shows the train on the x-axis, and then it shows how much the sound pressure level, the decibels, going along the train. And what you can see that there are quite a few peaks. Pretty much wherever there's a bogie, there's a peak in the sound being produced. Wherever there's a pantograph, there's also a peak in the sound being produced. And at the leading edge, so the nose of the train, there's a peak. And then most of the rest of the train, there's this reduction. And in fact, there's actually a reduction at the intercoach spacings at some point. So not the trailing edge or the leading edge of the two carriages, but the bit in the middle. That is actually a reduction. So even though the general intercoach spacing does produce greater noise in some regions, in other regions, there's a reduction. The aerodynamic noise spectrum of the high-speed train extends over a wide frequency domain and can be considered broadband noise, with the main energy containing frequencies concentrated between 800 and 4,000 hertz. It must be mentioned that the Doppler effect introduced by the train pass by is not taken into account in the spectra. So that's an interesting point. When you have, I mean, everyone knows the Doppler effect. When you have something traveling towards you making a noise, you're going to get an increase in frequency. When it's traveling away, it reduces in frequency. But considering that this is a broadband noise, it won't make too much of a difference in terms of the sound pressure level. If you have the weighted sound pressure level for human hearing, then that will make a bit of a difference. Just a bit on that. For those of you who don't know, there's obviously just general sound pressure level, which is what is registered with instruments. But then there's also something called the dBA, decibels A, and that's the weighted sound pressure level based on our hearing, because our hearing is not perfectly attuned to every single frequency. It's attuned to certain frequencies far better, certain frequency ranges. And so you can have a very high noise at, let's say, 50,000 hertz, but because our hearing can't pick it up, we don't care, we're immune to it. So that's what the weighted sound pressure level means to us. And the whole graph here showing frequency with this power spectrum density, so the noise effectively, decibels. And it is fairly broadband across the entire range, even from like 500 hertz to 5,000 hertz, it's quite high. It's 50, 60 decibels. So that's the end of this podcast, which is talking about the sound production from a high-speed train. The next podcast is going to be about sound reduction. So make sure to like and subscribe to this. Check out all the instruments we make at Premier Aerodynamics. Check out the courses we put on to make you a better analysis, and check out the conference we put on every year. I'll see you in the next podcast. Peace out.